Hello everyone, welcome to the Elman Prize Symposium. As we've just heard, the Elman Prize this year was awarded to Wei-Ji Ma, who is a professor of neural sciences and psychology at New York University. My name is Ronald van den Berg. I'm an associate professor at the psychology department of Stockholm University in Sweden, and I will be your session chair today. The symposium consists of a series of brief talks that will highlight both Wei-Ji's scientific achievements and his community building activities. The speakers include, besides myself, Janneke Jehe, who's an associate professor at the Donders Institute for Brain Cognition and Behavior in the Netherlands, Deo Lee, who is a professor of neuroscience at Johns Hopkins University, Wil Adler, who is a former PhD student of Wei-Ji and now works at the non-profit Center for Democracy and Technology, and Yael Niv, who is a professor at the Princeton Neuroscience Institute. The final talk will be given by Wei-Ji himself, in which he will advocate for a different incentive system in academia. Thereafter, we will have a brief Q&A session with Wei-Ji, so if you have any questions for Wei-Ji, please let us know so that we can give you audio rights during the Q&A session. So my own connection with Wei-Ji is that I was a postdoc in his lab in 2009 to 2012, when his lab was still at the Baylor College of Medicine in Houston. I had just gotten my PhD degree, and Wei-Ji had just gotten his very first faculty position, so I was actually his first postdoc recruit. Now looking back at it, it might have been a little bit of a risky and perhaps odd choice to do a postdoc in a lab that is headed by a guy who doesn't have any experience with supervising postdocs and also didn't have any extensive experience in running a lab. However, it turns out that, for me it has been a really good choice, because it became clear pretty quickly that Wei-Ji is not only a very good scientist and very hard-working scientist, he's also an excellent mentor and teacher. So I didn't only get a lot of work done with him in those years, I also learned a lot from him about good mentoring and teaching in a way that is not only focused on publications and the interests of the lab, but also has a strong focus on the careers and the well-being of the people in the lab. And that's something that I and many others really appreciate about his approach. So of course I didn't only learn about science when I was in Wei-Ji's lab, I also learned quite a bit about Wei-Ji's personality. And one of the things that I learned is that there was something mysterious going on sometimes in the lab. So we had these offices with very large windows, so you could see what was going on in the offices of people. And it would happen sometimes that I would approach Wei-Ji's office with a new plot or a new result, and then what I would see on his screen is a little chess playing window. But then as soon as I would enter the office, then suddenly that chess game window had been replaced with a Word document, and Wei-Ji would look like he was very busy with something. So it turns out that Wei-Ji is a procrastinator, and back then apparently he was ashamed of it and tried to hide it, perhaps not always very successfully, but it looked like something that he didn't want to broadcast to everyone. Nowadays, as many of you might know, it's something that he openly talks about, and it's one of the themes that he discusses in his Growing Up for Science seminars, which we will hear more about later in this symposium series. So the reason why I bring this up is that I think this is something that typically illustrates Wei-Ji, that he has this personal experience, in this case a bit of a negative experience, and then he turns it into something positive, a positive contribution by sharing his story with other people and helping them with their procrastination problems. Another thing that's a little bit typical is that he actually turned this into a science project where, with a student of him, they formulated a model to try to find a rational explanation for procrastination. And that's also something that you'll see back in Wei-Ji's work, that he takes these personal observations and then tries to find quantitative scientific explanations for them. So another thing that characterizes Wei-Ji is that he likes to have a lot of things going on at the same time. I remember from my time at Baylor, when his lab was still in its infancy, that he had this overwhelming, at least to me, overwhelming list of projects that he was working on, but he really seemed to enjoy it, and he really also seems to be good at handling all these things at the same time. If you look a little bit deeper though, then you'll see that a lot of the projects follow the same kind of philosophy, so which I illustrate here in these 3 points on the slide here. So Wei-Ji is not so much interested in injecting new phenomena, new effects into the literature, but he's mainly interested in deepening our process level quantitative understanding of known phenomena. And he does this in a way that he tries to cover all three of Marr's levels of explanation. So he's not only interested in the question, is something optimal or is it suboptimal, but he's also interested in the computations that go on behind in the brain and the representations that the brain has. And then at the deeper level, he's also interested in how all this links back to the neural level, which we will hear more about in the next talk. So the two fields that I've been working in together with Wei-Chi is perceptual inference and visual working memory limitations. And I'm just going to highlight a few of the things that we did. So the first study that I'm going to highlight is this study that we did on inference of sameness. So the question, how does the visual system determine if a set of objects are all the same or whether there are differences between the items, the visual items. This is a very basic and fundamental cognitive ability that William James was already writing about in the 1890s. And since then, there has been quite a lot of research on this ability. But one thing that characterizes the previous literature is that, first of all, most of it is qualitative in nature. And secondly, a surprisingly large amount had been done on non-human animals, not so much on humans. So here's a typical example of an animal study where animals are presented with these kinds of displays where either all the items are the same or whether we have differences between the items. And then they are trained to discriminate between them. So a few of the qualitative findings that were reported in the literature, for example, if you increase the number of items in the displays, it becomes easier. If you increase the differences between the items in these different displays, it also becomes easier. If you increase the amount of noise or blur in the items in the displays, then it becomes harder. So there were a lot of qualitative findings, but what was lacking was a quantitative principled theory, and that's something that we try to set out to find here, together with two colleagues from mathematics department at the University of Houston. So the approach that we took is the one sketched here, which is also very typical for Wei-Chi. You'll see this back in a lot of his work, where the first step is to define a simple Bayesian model for the task. So we asked, what would the Bayesian observer do? What would the optimal observer do in this case? Then we performed an experiment where we made sure that we would test the unique predictions of the Bayesian model, and then we would do a extensive model comparison where we compared the Bayesian model with models from the literature, but also with other models that we could come up ourselves. So one thing that we had to do is first parameterize these the stimuli, because the previous studies had mostly been using these picture stimuli, which are really difficult to model and also really difficult to control in an experimental setting. So the displays that we used looked like these ones here with these oriented ellipses, which we flashed very briefly so that there was a lot of visual uncertainty in the observers' brains. And the nice thing of setting it up like this is that we now had very tight control over the amount of differences between the items in the different trials. So we quantified it with a variance. So if you have high variance, they're very different. If you have low variance, it's very similar. And this, of course, would be the same trials or zero variance trials. So another thing that we could manipulate in these displays is the visual noise per item. And that's something that's important because the Bayesian observer makes very specific predictions about how the observer should deal with differences in precision between items. So in this case, we did it through the elongation of the item. So these more elongated items are perceived with less visual noise than these more blobby items. So you have lower quality orientation information for these than you have for those. And this is also something that you see back in a lot of Wei-Chi's earlier work, because again, this allows for a very strong test of Bayesian models, this reliability manipulation. So the optimal observer, I'm not going to go into detail, but what the optimal observer would do is to compute the weighted variance of the noisy stimulus observations and then compare it to a criterion that depended both on the amount of noise in the display, so determined by the elongation of the items, and the number of items, the set size in the display. And this makes it a really difficult task from a computational point of view, because if you vary the amount of noise or the set size from trial to trial, which is what we did in our experiment, then the observer should also change their decision criterion from trial to trial. And that seemed something that, we thought this might be too hard for humans, and we were not too certain to find actually Bayesian behavior here. So the experiment was very simple. We showed these displays very briefly, and then the question was, were all the orientations the same or not? And then we repeated this for a few thousand trials for each observer. So the main findings are that this kind of straightforward Bayesian model that we derived captured the human behavior very, very well. It captured the behavior better than all the other models that we tested. And again, that was a little bit surprising to us because we had not thought that people would be able to do this reliability weighting from trial to trial correctly in this kind of setting. And one thing that's really nice about this study also is that we were also able to use the same Bayesian model to explain the qualitative findings from previous animal literature. Okay, so most of my work actually with Weiqi was in the realm of visual working memory limitations. I'm very briefly going to highlight 3 of the contributions that we're proudest of. So the first one is that we introduced this concept of variable precision in 2012, where the idea is that instead of assuming that items in working memory are all encoded with the same amount of precision, as in the previous models, as in all models that were existent at that point, we asked what happens with the model predictions and the fits to the data if we let go of that assumption, and if we assume that there's random variability between how precisely items are encoded in working memory. So on one trial, for example, you could have one item that by chance got very little resource, low precision, and others higher precision. So this seems like a very subtle change. But also, I think it's also a very plausible thing because we know that there's fluctuation in attention and there's also neural noise, etc. So it seems like a very plausible thing, but it also looks like it's a very small change in the models. The nice thing, though, of this is that we were able to, so this little change in the model allowed us to describe visual working memory, data on visual working memory tasks better than previous models, and previous models meaning slot models. So we did no longer need this notion of slots, which was very dominant in those days. It actually still is, but we showed that you don't need this notion of slots as soon as you assume that there's variability and precision in the brain. So another study that we did was a factorial model comparison of visual working memory models, and this was a direct continuation of the previous study. So in the previous study we tested 4 models, but we also realized that those 4 models actually consist of multiple components, and that each of those models can be dissected into different, into their components. And once you've done that, then what you can do is recombine all the components in many more different combinations than the original set of models that you had. So for example, you then get models that don't only have variable precision or only slots, but you could have models that have both variable precision and the notion of slots. So we dissected models into components, then recombined them into 32 models, and I believe that the original model space was only 6, so we had 26 new models, and we actually found that the data were best described by one of the new models that we found by combining these components in new ways. And one thing that I think is really neat about this approach is that instead of focusing on specific models, what you can now do is quantify evidence from model components. So you can ask, for example, how much evidence is there for the notion of slots regardless of any other assumptions that we make in the models? Or how much evidence is there for variability and precision, etc. So the last one is a study that we published only a few years ago, where we formulated a normative explanation of set size effects. So a normative explanation for why precision in memory decreases with the number of items in memory. So for the sake of time, I won't go into detail, but the short story is that we reformulated this effect here from being a constraint in the brain to being a cost, a rational trade-off of 2 different kinds of cost in the brain. So it's something that the brain determines itself instead of it being a constraint. That sounds a little bit vague. You can read the paper if you want to know more about it. I'm over time, so I'm going to stop here. I just want to end by congratulating Weiqi again with this very well-deserved prize. And also, I would like to thank him for all the guidance and friendship and all the work that we've done over the years. So thank you very much.